Hello friends, in today's class we are going to talk about multi-level page table. So welcome here, and we are talking about with the multi-level page table. And since we have already seen the one level page table, we have to first see the what exactly the problem lies with one level page table. Okay, and here are a few points that has been summarized here is this the first point summarize the size of single level page table. Okay, and that becomes huge actually. So most modern computer systems support a large logical space, let's say 2 to the power 32 to the power 64 logical address space. This is your logical address space. And in such an environment, page itself becomes excessively large. For example, consider a system with 32-bit logical address space, and if the page size is 4 kilobytes. So if it is having 32-bit logical address space, which is very reasonable, okay, in today's modern computer, if we have 32-bit logical address space, and we have 4 kilobyte, that means out of this 12 bits will be assigned to the page offset, and 20 bits will be assigned to the page number. Okay, so number of pages will become what? Number of pages is equal to 2 to the power 20. This many pages will become, and there will be 2 to the power 20 page table entry, right? So there will be 2 to the power 20 page table entry. Now suppose each page table entry size, okay, suppose each page table entry size is equal to 4 byte. If it is the case, so this will become 4 byte into 2 to the power 20, and that will become 4 megabyte. This 4 megabyte should be contiguous. It is not the issue with 4 megabyte, but it has to be contiguous. And this only needed for what? Only needed for this page table. Okay, we only need this only for the page table. So that is the thing written over here, and clearly we would not we would not want to allocate the page table contiguously in the main memory. Okay, one simple solution is that, like here, availability is one thing, and we have already seen some disadvantages with the contiguous memory allocation. Okay, contiguous memory allocation, and that problem was the creating holes. And right now we are in the non-contiguous using paging scheme. So let's also divide this this entire page table into smaller pieces. Okay, smaller pieces. Okay, and that is what it says that. And let's have a there are these are the several ways to accomplish this division. Okay, so there are various different ways we can accomplish this division. Okay, so divide the pages into smaller pieces. That is the idea, and that leads to the hierarchical page tables. Okay, hierarchical page table, which breaks down the logical address space into the multiple page table. Okay, simple of this technique here in this case is two-level page table. Okay, one of the simple technique here in this case is two-level page table, and then this concept can be extended. Okay, so there's two-level page table, and then this concept can be expanded. We then page the page table. Okay, we are again simply dividing page table. We are simply dividing page table into what? Into pages. Okay, into pages. Fine. So that is the idea here, hierarchical page table, and we'll go with the first one to start with what? To start with the two-level page table. Two level page table. Okay, hierarchical paging. So in this case, I've already told you two level page system, which is a page is itself is page. Remember our example, 32-bit required 32-bit machine with the page size of 4 kilobyte. Logical address is divided into page number consists of 20 bits and page offset consists of 12 bits. Because we page the page table, page number is further divided. Okay, now we are paging the page, so now this will be further divided, and in this case, this is the situation, the common situation that we have already seen, and this is the situation which is having a page number. Till now we have seen many times, and then we have seen page offset. So this is a 12 bits. And here there is a page number is of size with 32 bits, it will become 20 bits. The total size of the memory, that is your 32 bits. Okay, now further what we are going to do, we for hierarchical paging, we are going to take this 20 bits and further we are going to divide this thing. Further divide this 20 bits. Okay, how? This is the example of it. So this is the visualization of it. So there will be an addresses will be there. Now this will previously what in one level page table, directly what we get in this case is it is consist of address of a frame number. Okay, so this will be a frame number, and that frame number directly combines plus with your offset, and that become the address, physical address. Here we will get again, we will get in outer page table, again we'll get a base address. Okay, and if I go to this, again I will not get this address, but again I will get the base address. Okay, so now we are having a base address, like here this is the address in the memory, somewhere in the memory another page will go to another page, and here that will now finally go to 1. It is 100, and I'll go to 100 in that case. So I'll get an address, I'll follow this address, I'll get 100, then I'll get to this next address. So as I told you, just logical address to page number is consist of 22 bits, page offset is consist of 10 bits. Since the page table is paged, the page number is further divided into this part. Okay, 2 to the power, let's say a 12 bit of page number and a 10 bit of page offset. Okay, 12 bit of page number. Okay, so this is now further we are doing the same thing for that 20 bits. We are again dividing further into page number, and we are further dividing into what? Page offset. Where P1, okay, P1 is the index of outer page table. Okay, and P2 will become what? P2 will become index of, P2 is the displacement within the page. P2 is the, okay, P1, and now this is the point of turn. P1 in the index in the outer page table, and P2 is the in displacement offset. Within the page, in the inner page table. Okay, this is known as forward mapped page table. Okay, so now this index and outer level page table displacement in the single inner level page table should be learned in this way. Okay, now we have two page table. Okay, at two page table we are having. So there is a P1. So what we'll do here in this case is P1 is the index. So there will be entry like page number. We have already seen the entire thing was a page number. Okay, so now this entry is this entire 20 bit is suppose 20 bits was 4. So we'll go to the PTBR plus 4. Okay, ptbr plus 4. Here also we'll do the same thing, but here in this case is displacement. This is index of the first level, ptbr plus I will take p1 and I'll get to this address. Now this will consist of some 2000 value, some value. Suppose it is consist of 2000. Okay, now this 2000 is what? This 2000 is again a base address. Okay, this 2000 is again a base address of second level page table. Okay, so this 2000 is again base address of the second level page table, but now this p2 will become the displacement. So now this will become what? 2000 plus p2. Okay, I hope it is clear to you. Finally we'll get the frame number here. In this case we will get the frame number, and that will be combined. Usual what we are doing in this case is frame number combined with what? Combined with D, it will become your final address. This will become the final address. Okay, so this is my address translation schema, and what we can say here, let's have a 64-bit logical address space. Page size is 2 to the power 12 byte. So this is a 12 byte, and we are remaining with what? 52 bits. Okay, 52 bits, which can be further divided into 42 bit and 10 bits, outer page table and inner page table. So inner page table, the two level page schema, and inner page table could be 2 to the power 10 4 bytes entry. Okay, 2 to the power 10 4 bytes entry. Outer page table will have 2 to the power 42 entries, or 2 to the power 44 bytes. Okay, so 2 to the power 42 entry. Into each entry, if it is correspond to 4 byte, then it will be 2 to the power 44 byte. Okay, so now again we are back to the same situation, that again the outer page table becomes large in size. Okay, large in size. So roughly what we can do, we can again, one solution is have a second outer page. Okay. Okay, so now so this can be further, we can have as many as we can have page table, page levels. Okay, so now this is a two level page schema, that outer page, inner page and offset. Second outer page, and then we have a outer page, and then we have an inner page, and we have a offset. So we are keep on dividing this thing in this case. Okay, so that is our discussion of how we are dividing this again, because we are leading into the problem of contiguous memory allocation, and we required 4 MB contiguous space. So we decided to page the page. Okay, we then page the page table. Further we divide it, and how different ways we can divide is this 20 bits that is coming here, that we are dividing here in this case, and this is the overview of it, and this is the division that we know as forward page table, and this is an example here that how basically this division works. Further we find here that if there is a 2 to the power 64 bit logical address space, outer page table becomes very large. So we can go and further divide this, and we can have as many as page table. The next section we are going to solve few questions related with this page table. Okay, so that's all for this section. Thank you.